And we'll go through these pretty quick. Okay, let's see. I think I got it on the screen now. Cool. So the limit comparison test, honestly, the limit comparison test works every time. You don't ever have to bother with the direct comparison test. That direct comparison test I think is easier and I think logically makes a lot of sense, but sometimes it won't work if that inequality falls the wrong way. But this limit comparison test, it does work a whole lot more often. It doesn't end up being a 50-50 coin flip. So if you want to just always jump first and do the limit comparison test and kind of just skip over the direct comparison test, that would be fine. I like knowing both, because sometimes I think direct comparison is easier, and logically I think that would make sense. But if you want to just always use limit comparison, that's going to be fine. Anyways, throughout this, you need to remember that A sub n, that sequence and that corresponding series, A sub n, just like how A comes before B, A was there first, so I'm going to consider A to be the original. B is the one that I'm going to choose to compare it to. So A is the original, B is the one that I create to compare it to. Let's read it. It says, if I have the limit, I take the original, divide it by the new one. Remember, A comes first, B is after. So if I put the original and I divide it by the new one, if I were to take that limit as n goes towards infinity, and I get some value L. And that L is just some number, but that number had better be finite and positive. If I were to evaluate this limit, it doesn't matter what that number is. It could be 1, could be 1/2, it could be 50, doesn't matter. As long as you get something that's finite and positive, then, let's read it, the two series are going to either both converge or they're going to both diverge. I like to think about it as they're going to be the same. They're going to both do the same thing. They're both going to be finite, they're both going to converge, or they're both going to be infinite and diverge. So the limit comparison test, I throw the original, divide it by the one I choose to compare it to. I take the limit as n goes towards infinity. If that limit value ends up being finite and positive, then those two series, remember the original and the one you chose to compare it to, they're going to do the same. Now be careful. If this limit gives you something like 0, or if this limit gives you a negative number, or if that limit gives you infinity, you cannot logically conclude anything else. What this test says is, if the limit is finite and positive, then the two things do the same. You cannot conclude anything if the value is not finite and positive. It doesn't mean, hey, if the limit's infinite, then they're going to be different. No, you don't know that. That could be true, but this test doesn't tell you that. All this test tells you is that if the limit is finite and positive, then the two will do the same. It doesn't tell you what happens if this isn't met. So be careful not to overextend this limit comparison test. It only works if that limit is finite and positive. All right, so let's go through, do these couple of examples, then we'll be done with the comparison tests. All right, first one. Here I've got this weird, ugly, rational, looks like, into the fourth plus 10 over yada, 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 right? That would be kind of hard to do a direct comparison test to. I guess you could try to do something like this, but then you'd be a little bit in a trouble trying to figure out which denominator is bigger, so on and so forth. So direct comparison test isn't super easy for something that's a little bit more complicated. So here the limit comparison test is a little bit the more way to go. Right, so let's compare this to n to the fourth over n to the fifth. This is, again, kind of like the simplest version of this original. You definitely kind of just disregard any of the extra stuff. You just find the biggest term in the top. You find the biggest term in the bottom. You can put the 4 in the denominator if you want. It's not necessary. It's not going to change whether that limit is finite or positive or not. So again, find the basically the parent function of this original series, which is just n to the fourth. You don't really need the 4. You can put it if you want, but you don't need it. But I'm going to choose to compare this to n to the fourth over n to the fifth, which is like the parent function of my original, the simplest version of it. Here, this would reduce to 1 over n, right? N to the fourth over n to the fifth would reduce to 1 over n. That's the harmonic series, which I know diverges. You don't have to say by the p-series test. Just calling it the harmonic series is enough to say therefore diverges. But it does diverge by the p-series test or by the integral test if you even want to go that far. So here's my original. I don't know what it does, but I'm trying to figure out if it's convergent or divergent. Here's this other one that I'm going to compare it to, which I know diverges. Let's now go through and do this limit. I'm going to put the original, divide it by this new one, and if that limit is finite and positive, these two do the same. So here we go. The original over the one I choose to compare it to. Just do your little sandwich trick. Remember, outside two go to the top. These middle two layers go to the bottom. And then you can quickly and easily evaluate this limit. Since the top is degree 5 and the bottom is degree 5, you just look at the ratio of the coefficients. And so here, this limit is going to end up being 1/4, which, oh, look at that. That's positive. And it's finite. Oh, I said that backwards. That's okay. It doesn't matter. It's finite and it's positive for sure. 1/4 satisfies both of those conditions. So since this limit was finite and positive, I know this series and this one do the same. Now be careful. Finite and positive doesn't mean they're always going to converge. Finite and positive mean the two things do the same. Since I know this one diverges and I know the two are going to do the same, now I can logically conclude that my original series must also diverge by the limit comparison test. So be careful. It's really tempting to say, okay, finite positive, therefore converges. No. Finite and positive means the two are consistent. They behave similarly. So if you know this one diverges, the other one diverges. Or if this one would have been convergent, the original would be converging. So just be careful. Finite and positive means they do the same. You still have to figure out what that same thing is by figuring out this thing that you compare it to, whether it converges or diverges. I think there's only one more. Yeah, and then let's go for it. La-da-da. Okay, here's the next one. This one, you could try to do the direct comparison test, but the inequality is not going to end up falling the correct way. You'll end up with something like, oh, the bigger one it diverges, so you don't know anything about the smaller case. Or maybe the smaller one is convergent, so you can't logically conclude about the bigger one. The inequality just doesn't work for the direct comparison test. It ends you in one of those two inconclusive cases. So we can just jump to the limit comparison. Remember, if you always want to jump to the limit comparison, you can. But let's go for it. I'm going to compare it to the simplest version of itself, 1 over n cubed, which is a p-series. The p-value is 3, which is bigger than 1. So I know this thing, which I choose to compare it to, that's going to converge by the p-series test. Now let's go through and do my limit comparison test. Remember, original goes on top. The one you choose to compare it to goes to the bottom. Spoiler alert, if you flip them, it really doesn't cause that many problems, but then the test puts the original on top, the new one on the bottom. If you were to flip them, shouldn't be the end of the world. But here we go, I take my original on top, the new one on the bottom, just do my sandwich trick to simplify it. Since it's cubic on top, cubic on the bottom, the ratio of the coefficients 1 is going to be that limit value. 1 is both finite and positive, so this and this are going to do the same. Since I know this converges, my original series must also converge by the limit comparison test. Oh, let's see what I got as this note. So here's what the inequality would have played out as. Since this has the smaller denominator, this would be the bigger fraction. Remember, this was convergent. So you know the smaller one is convergent. That doesn't logically dictate anything about the bigger one. So the direct comparison test wouldn't have worked. You wouldn't have gotten anything conclusive, but using the limit comparison test does end up telling you that this original series is going to have to do the same as this one that I chose to compare it to, so I know this is going to converge by the limit comparison test. If you want, you can always skip the direct comparison test and just use the limit comparison test. I like to know both because I think the direct comparison is easier and logically it makes more sense, but it doesn't work 100% of the time. This limit comparison test, remember, if the limit's not finite and positive, this test does not work, but it does work a whole lot of the time. All right, so that's your two comparison tests. Hope it made sense.